In this video I'm going to talk about scale factors. This is the way that cosmologists calculate where an object is going to be at some time in the future or the past due to the expansion of space. Remember that the expansion of space is carrying everything apart from everything else. That is to say, all things that are far enough apart they're not chemically bound to each other or gravitationally bound. So the distance between any two objects gets bigger, and the more space there was between them to start off with, the faster it grows. So how can we express that mathematically? Well, if we have a bunch of objects in space, galaxies, nebulae, clusters, whatever they might be, we can set up some coordinates. Coordinate axes, so let's say x, y, and z. And any given object has got coordinates. So its position right now, position 0 equals x, y, z. That's its position now, but how's its position going to change in the past? Well, the way we're going to do this is simply multiply the positions by an extra factor. So we'll say the position at some time t is going to be the position now multiplied by a constant. A constant that varies with time. So it's constant in the sense that all different galaxies at the same moment have the same constant, but it's not constant at different times. So this terminology, the brackets t after it, means that this is something that depends on t. It's a function of t. So the position as a function of t equals the position right now times the scale factor, this constant a, which is also a factor of t. What do we know about a of t? Well, we know space is expanding at the moment, so a of t must be getting bigger. So as a function of time, let's say that's the present day, and we'll define the scale factor at the present day to be 1. And we know the universe is expanding, so it's going up like this. So in the future, a of t will be more than 1, and in the past, it'll be less than 1. So that's how we calculate where things are going. So let's say we wanted to know where a given galaxy was going to be 2 billion years in the past. We would have to know what the value of AT back then is. At the moment, we don't know the exact function of AT other than it's going up and down. But if we knew what the scale factor was back then, the position back then is just equal to the position now times the scale factor back then, which will be less than 1. So you're multiplying the current coordinates, x, y, and z, by something less than 1. So its new position will be a of that time x, a, y, and a, z. And as a is less than 1, that means all three coordinates will be less. So everything is indeed closer together. So how does a scale factor relate to redshift? Well, imagine a photon of light. It's a wave, electromagnetic wave, and with our spectrograph we measure the wavelength lambda. Now the redshift is defined as the change in wavelength divided by the wavelength when the light was emitted. So how's that going to be affected by the scale factor? Well, as the universe expands, it's going to stretch the photon. It's going to pull the front and back further apart from each other because they're not bound to each other. So the wavelength of a photon at some time t is going to be equal to the wavelength now times a of t. So let's put that into here. The redshift is equal to the change of wavelength, which is the wavelength now, minus the wavelength when the light was emitted at some time t, which is lambda t, which is lambda naught a of t, all divided by the wavelength when it was emitted, which once again is lambda naught a t. So all the lambda naughts cancel, and we find that the redshift is equal to 1 minus A of t, the scale factor, all over A of t. We can rearrange that, multiply both sides by A of t, and we get Z A t equals 1 minus A t. Move this across here, so you get 1 plus Z A of t equals 1, so A t equals 1 over 1 plus the redshift. So if you know the redshift, you can calculate the scale factor, and if you know the scale factor, you can calculate the redshift.